In this video I'm going to look at the acid dissociation constant, Ka for short. So you can see on the board there I've got the simplified version of the dissociation that exists when a weak monobasic acid is put into solution. So we've got partial dissociation of HA and in equilibrium with the ions H plus and A minus. You can see in orange there I've written down Kc is the concentration of the products over the concentration of reactants. And if you remember, Kc, the equilibrium constant, gives us a measure of the extent to which the equilibrium is either on the right hand side, moving forwards, or on the left hand side, going backwards. So we can do the same for an acid. So instead of Kc we put Ka, and it looks like this. So you can see we've got our two products here, the concentration at equilibrium of the H plus ion multiplied by the concentration at equilibrium of the A minus ion all over the concentration of HA, products over reactants. So there's two specific examples now. We've got ethanoic acid and methanoic acid. Ka expression for ethanoic acid would look like this, and you can see over on the right hand side there its Ka value, numerical value, comes out at 1.7 times 10 to the minus 5 moles per decimeter cubed. And if you don't like standard form, there it is in full. Methanoic acid, Ka expression would look like that. So it's the same format. It's the equilibrium concentration of the products divided by the reactants. And you can see its Ka value is 1.6 times 10 to the minus 4 moles per decimeter cubed, or 0.00016 moles per decimeter cubed. So what's the significance of the Ka values for these two acids? Well, the Ka for methanoic acid is actually a larger number than the Ka for ethanoic acid, and so that's telling us that methanoic acid must be a stronger acid. It must be more dissociated. Now, similar to pH numbers, we actually have something called a Pka number, essentially doing a similar sort of thing, whereby it takes rather cumbersome, in the case of pH, rather cumbersome H plus concentrations and turns them into sort of simpler numbers. So we get the pH scale going from typically 0 to 14. Pka is a similar sort of thing to pH. So we take a rather awful looking Ka value, so this or this, and we turn it into a more manageable number by doing minus log of the Ka value. You can see I've worked them out. We get a Pka value for ethanoic acid coming out at 4.77 to 2 decimal places, and for methanoic acid we get a Pka value of 3.80 to 2 decimal places. And again, similarly with pH, the lower the value of Pka, that means the higher the value of Ka, and therefore the greater the extent of dissociation. And again, just as with pH and H plus concentration, you can go backwards. So if you know the Pka value, you can work out the Ka value by performing this operation here. So Ka is 10 to the minus Pka.